6.1, which is basic statistics. We talked about calculation of the mean, standard deviation, some of the quantile, right? We have a visual presentation of the data. We can present it with a histogram, dot plot, stand plot. So that's 6.1 go over some descriptive statistics. 6.2 we went over the order statistics, right? 6.2 was the application part. If you have a data set like the raw data, you want to be able to order the entire data set. We were naming them Y1, Y2, Y3, Y4, right? With that, we can define the percentile. We went over calculation percentile in 6.2. 6.3 went a little bit further to be more specific about the probability density function for the Y, for the order statistic, right? So we did that, and we also have the expectation of Fy, which is F function is the cumulative distribution function of the original data set. Fy is converting it to a uniform distribution. So the expectation of it was like a R over n plus 1.
Yes.
That was our expectation. So that's 6.3, which is like finding more information about behavioral Y, like older statistics. And then we went on to 6.4. 6.4 was estimator, maximum likelihood estimator, and which allows us to estimate any parameter that we had for a distribution. You get your data, and you think the data has follow exponential distribution. Then you gotta find the mean, which is a parameter for your distribution, right? And then estimating that parameter, you have to use a certain formula, which involves all the raw data that you had. So we can have different, for different distribution, we have different estimator using the maximum likelihood method. But there are occasionally when the distribution function itself, the density function itself, involve a really complex coefficient, and we will not be able to calculate the maximum likelihood estimator. So we will have the second method. It was method of moments, right? We will pair the theoretical moment from the distribution function with the empirical moment from the raw data, and we set them equal and solve for the parameter. That ended up giving us the estimator. But then we also have a problem if like you can't find the moment. Method moment, you use the moment. But if the function itself, by definition, does not have a first moment or second moment, we have a problem. So that brings up the third method, what's called percentile matching. So you set up a meeting of your data using the original distribution, pair with the meeting of your raw data, right? And set them equal. We can find the estimator of the meeting. So that's 6.4. And when we're last Wednesday, before the quiz, we went over the simple regression, right? Simple linear regression with the example we had. If you think your regression relation between two variables, let's say x variable and y variable, if we think they follow a formula like y equal to alpha, we have a model for distribution. So let's say we have a lot of data, like say x1, x2, and then xn. Then we have a set of data for y, that y1, y2, they're pairs, x and y, they're pairs, and yn. So suppose at x and y, you draw what we call a scatter plot. If we feel like the plot seems to be showing a possible linear relation, scatter plot you can draw with R or any graphing tool. Scatter plot essentially is drawing all these xy pairs into dots, and then we see identify relation. If the relation seems to be possible, we set a model like y equal to alpha plus beta times x minus x bar. Okay, we set up a possible model, and in here the x bar is dependent on by all this x value and beta. X bar is the mean value of x. X and y, there are supposed to be possibly all these data, And of course, this data doesn't follow the equation exactly, so we have the error term, L, E, I, Y, I, and X, I. So in this model, the Xi, Yi, X bar, they were all given from the raw data, and then we can calculate a formula for alpha and beta. And what we have is the alpha actually equal to the Y bar, sample mean for the Y value, and beta we had a specific formula for it. The numerator was like summation of Xi times Yi. Minus the summation of Xi, which is this divided by n, which is really the Y X bar, times the summation for Yi.
Yep.
This is divided by summation of Xi squared minus the summation of Xi squared over n. That was our beta formula. And so this is what we did in section 6.5 with a simple linear regression. The goal for any regression is to identify relation between x and y. Yeah, linear regression. Any questions?
The formula for sigma squared, like n times sigma squared, is equal to summation yi squared plus or minus 1 over.
I think this is summation of y I minus the y being estimated using the formula, and then square, and then divided by n. Or n minus 1. Yeah. It's a variance. So isn't variance supposed to be data minus mean square and then divided by, we can see. We actually have a formula for this. Yeah, in the numerical example, we had a formula for this. This is divided by the sample size n. I think we have n pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So that's the overall sum of squares.
Yeah, but the formula I have is like a lot more complicated. It's like 1 over n times and the summation of y sub I minus the estimation for alpha minus the estimation for beta times x sub I minus x bar squared.
Was it also in the text? You mean this one?
Yeah.
That's one?
Yes.
It's the same thing. You see this is the yi, it's your raw data. And now we see y, see you already have the alpha plus beta x minus x bar. That's the yi.
Oh.
So that's essentially y minus yi hat. That's the estimated y, that's the original y. The differences between the real y with a predicted y, that difference is what we call the error term. Like if you're using this formula to estimate your y value, you're making a small error. So this is calculate that error and then square that divided by n.
Okay.
So in sense, it's still a variance calculated by raw data minus the mean square and divided by n. That was the sigma square.
Okay. But you're still supposed to, for that, you're still supposed to use the individual x sub I, right, for each one?
Right.
Okay.
Yes. But they follow the same formula. If you are using R, they can be calculated pretty quickly. I think I went over this as you guys were doing the quiz last week. I had a example showing what we're doing. Okay, so what you can do is you enter the X data, you add, I was double checking if my data is right. What happened there? So you enter the Y value, and that's X and Y. You can then find the linear model between the X and Y, and you can plot it. And I was trying to figure out what's what, and equal to 10 actually. So I find the beta using the beta formula that we had in there, which ended up being the same as what's going represented by the LM. LM is the linear model given by R. Actually, these two are identical. That was the beta formula. So I find a mean, and I find a mean for X and Y, and that's the formula we end up having using the textbook formula. So here I try to calculate the residual in the layout. If you run the linear model function, they give you the Y value, the X value, also the estimated Y value. So it automatically calculates the residual, which is the Y minus the Y hat.
Okay.
It's being calculated as called residual. So you can find the residual data. This is square the residual, and then add it all together. That's called the sum of square of the error. So SSE represents sum of square divided by 10, which is what we wanted in the question. That's the sigma square. So we can also, this is just example showing you how to calculate the error term ourselves with the R. If you want to see it, I can show you what was the coding part. I guess we can put the code somewhere else, and then I can move on to the R coding online. What was the link? All right. We can do it one by one. So this is our X data. This is our X data. I was trying to confirm that this is the same data as we had over here. See, this is our data. The summation is supposed to be 683. Occasionally I made a mistake of entering the wrong data, so I was like, maybe I should double check. So I did sum of X. Maybe I should. Can you see it? So we can find the summation, and that will tell me that if I enter the data properly. So if the summation gave me 683, so I know the data would be. You see?
Yeah, I see it. Okay.
So basically, that's how we enter the X data. You can do the same for the Y data. Well, let's skip the summation part. So we enter X and Y, and then you can plot it. You basically plot the Y value and X. I guess I should do X and Y. It plots the scatter plot for you. You can also let the computer change so this is our X value, and this is the Y value. It shows like a rough positive slope in the graph, right? So we're going to try to find the equation of the line. Remember for this this is our formula. We're going to find the X bar. This is the X bar, and this is a Y bar. Both of them supposed to be part of the equation. So we can let the computer do the calculation. So we would, the X bar is supposed to be in the mean. So we find the mean of the X value, and we find the mean of the Y value. And that, of course, you can calculate by hand, but this does definitely save you time. We end up getting this, and that's exactly the same as you see in the textbook solution. So that's our X bar, and then we also have the Y bar. That's X bar, that's Y bar. Okay. And then we also have the beta, and I'm gonna just let the computer do the calculation. So we're gonna run a linear model, Y tilde X. So you run the linear model, it's just gonna tell you the slope, which then is the 0.7421, the beta, and it's the same beta that you see in the textbook solution. It's the beta value. Now that we have all that, we have the beta value, we have the X bar, you have the y part that you can write your equation on. But if you see, if you have this multiply that and then combine, it's going to be a different number. So in the linear model being present, it's actually 7. That's an intercept. All right, then about the sigma, and that it's a little bit more complex. So I'm going to save the result instead of output. So now we don't see it because it's being saved in. There's no output, but it's only in A. So we can actually see the result. For example, let's say I want to see, you use a dollar symbol to ask the computer to give you more of what's inside A. So residual. All right, so I'm going to ask the computer to show me what was the residual. So this is the residual. So we will take each y value, subtract their calculated y value using the linear regression model, and this is a residual. Theoretically, the residual should have the mean 0. Remember, it's supposed to be a normal distribution with variance sigma squared, and the mean is supposed to be 0. So I did go ahead and calculate. I was trying to see if the model is right, so I calculated the mean of the residual. Oh, to make sure the pronunciation is right. So here we have, it's not exactly 0, but it's pretty close. See 3.55, 10 to the negative 16. You can almost think of, yeah, it's almost think that is equal to 0. So the residual seems to be okay. It does have a mean 0. And if we want to find a sigma square, we can, I guess it's kind of a long, I'll just call it RE. And we can find the sum of the RE data. Just try to name it differently so it doesn't, every time you want data, it's a little bit, so that what happened there. It doesn't look right. Oh, I'm supposed to square that. Still does not look okay. Alright, so that's the numerator. We can compare with what we have in the book for the 7. Okay? And that's the summation of square. We have to divide it by 10 to get the sigma square.
Yeah.
So I guess the sum of the residual squared divided by 10 is the sigma square. All right, so that's about 21.77. Just want to verify that what we have in the textbook example is actually verified with the programming R. Any other questions?
Nope.
Okay. So today we're going to move on to 6.7. See if it's still recording. 6.7 is called sufficient statistics. All right, so let's define this first. All right, so we're going to look at the probability density function of a distribution. Suppose you have, this is a definition using the factorization theorem. It says you get a raw data, a random sample of, no, this is not a random sample. They're not independent actually. So suppose they have a joint probability density function. So x1, x2, xn, they have a joint probability density function with one parameter theta. Okay. So suppose we are able to factor this. Y equal to u, x1, x2, xn is sufficient for theta if the function can be factored. So let's say we can factor the density function into 2 factors. One factor contains information about theta and u. The other factor contains no information about theta, only information about x1, x2, and xn.
Okay.
In this case, the u is called sufficient for theta. Question? So we end up creating a function. That's basically what we're talking about in sufficient statistics. So in any density function, you try to think a way to factor the density function to make sure the parameter is, the theta is part of one of the factor, and the other factor, the rest of the factor has no information about theta. And then the one that has theta will contain a function of x1, x2, xn. This u is called sufficient statistics. How's that useful? And let's look at examples of sufficient statistics. We start with the Poisson example. All right, suppose x1, x2, xn denotes the R random sample from a Poisson distribution. Poisson distribution has one parameter to estimate, that's the mean. All right, so for x1, we have fx1 lambda, fx2 lambda, fxn lambda. They all follow the same probability function. That's a Poisson probability function. So each one of them, you can write it out as lambda to the power x, e to the negative lambda over x factorial, and we are multiplying n of them together, which is this. So in here, we're going to try to figure out which one has lambda. Remember, the lambda is a parameter. You want to factor out the part that has lambda, and the one that has no lambda, we will collect them and combine them as another factor. So now this is a classification. This one has lambda, that one has lambda. This has no lambda. So we push all these into this separate factor, and now here is the rest is what we call the sufficient statistics. At least I can write on top of it. All right, so after this is similar to what we did in the maximum likelihood estimator, right? The common practice in maximum likelihood estimator method, we try to multiply the density for each variable, and that's for x and that's for x2. We multiply them all together. That's used to be the one that we call lambda likelihood function for lambda, right? If you try to estimate lambda. So now, again, we want to find any part that has lambda. We're going to put it all together, which end up being here. So now you have two factors. This one has lambda. Now this factor has no lambda. Lambda is a parameter. So the one that has lambda, you see we have, this is the x bar, all right, and then that's just the n times lambda. N is really number of variable there, and this one is really not of our concern. So here it looks like the x bar is the only thing that relates to lambda in the whole likelihood function. So from our definition, we would see that x bar is sufficient. It is a sufficient statistic for lambda, which means if you are trying to find the value of lambda, all you have to have is x bar as far as estimating lambda. So, a sufficient statistic may not be the calculation formula for your parameter, but it's like the key part of your formula. Maybe you have to divide by it, maybe you have to multiply by something, but that's the majority of the information that's not being contained in the sufficient statistics. Any questions so far?
No.
So we're just defining it. This is true factoring of the likelihood function. Now we look at the second example. This example, we have a normal distribution. So we're assuming that this normal distribution has a variance of 1. So in this case, the only thing we need to estimate is the mean now. So from the same distribution. So we're doing the same thing. We are going to try to find which factor actually have the mean that allows us to make a estimator out of it. Okay, so right here. Now, so that's our parameter. Okay, so let's say they all follow the same distribution. So this is a density function for, I guess it's for all of them. So you have, it's it's really a multiplication, right? You have density function for x1, density function for x2, density function for xn, and you multiply them all together. Some of the factors are the same, so you raise the same factor to a power, right?
Wait, why did you?
That's really the likelihood function for mu. You have a question,
Oh yeah. I'm with you.
right? So if you only have x1, that's 1 over root of 2 pi e to the negative x1 minus mu squared over 2. If you only have x2, it's 1 over root of 2 pi e to the x2 minus mu squared over 2. That's because each one have the e to this power, each one have 1 over root of 2 pi. So they all raise to the power n, and this is summation in the exponent. This is really the multiplication of all this density, and that's our likelihood function. So now this joint density function or likelihood function, we want to find out which part has a mu, which part has no mu, so we want to find a way to factor it. So what happened is we actually inserted a minus x bar plus x bar. We end up getting this. And the part that has mu is this part. So we're going to separate the exponent here. Part of the exponent is summation between these two exponents. So this is the part that has mu, and we factor it outside. And this part has no mu, which is this part. This part has no parameter mu, and this is the one that concerns the mu.
So I have a question. Is the how can you split them up like that if they're being added together? How can you split them together into a? Because it's ex.
Yeah.
But my problem is that like there's a square on the outside. So like is x minus mu squared plus is x bar minus mu squared plus x sub I minus x bar squared equal to x sub I minus x bar plus x bar minus mu squared?
Yes, with the summation in there. You can carry out the calculation like algebraically look like this. So you would have summation x minus x bar xi minus x bar squared plus 2 xi minus x bar, and then x bar minus mu, right? The middle term, and plus the x bar minus the mu square. It will look like this after expanded. I mean, this part, it has a square, right? Expanded, it looks like this.
Yes.
The first one, we had this first one would equal to a summation of xi minus x bar square. The second one will be plus 2 times summation xi minus x bar times x bar minus mu. Alright, and then plus summation x bar minus mu square. I think the middle term equal to 0, because if you see the summation has index I, but x bar has no connection with I, so x bar minus mu will be a common factor. You factor the x bar out, and then what happens is this is the summation of xi, and this is summation of x bar. Summation of x bar, which n equal to n times x bar. But summation of xi also equal to n times x bar. So this equal to 0. Hope that makes sense. So it looks like this 2 times.
Yes, that makes sense.
Right, you factor this out, and then you end up having summation of xi minus x bar, with I being the summation index. So the summation of xi is n times x bar. The summation of xi is also n times x bar. So together, this part actually equals 0, even though you factor a common. happened is you were able to separate this two, and then this one has no mu, and this one that has mu, which gives us the sense that mu, to estimate mu, the only thing that you need is x bar. So x bar is considered the sufficient statistics for mu, and then the rest is just out there as a factor.
Okay.
That's our determination for sufficient statistics for mu. And so we have this conclusion that says that x bar is sufficient for mu. Okay. And that's our second example. So then you can see factor of the likelihood function or joint density function does provide information about how would be a good estimator, what would the part that contains the possible information for a parameter. And this is another example, which is the Bernoulli distribution. Bernoulli distribution have a random variable that takes on two values, 0 or 1, right? If x equal to 0, you have 1 minus p. If x equal to 1, the 1 minus y is gone, then you have p. P or 1 minus p. So this is the one that's the kind of example I hated, because it looks like it's really complex. Power x and power 1 minus x. But when you think of it, this probability is either p or 1 minus p, is what it is there. All right, so we have a random sample of size n. Each one have the same probability distribution function. So if you want a joint probability mass function, then you have this for each x1, x2, and xn. So again, we're looking at Bayes multiplication. T is raised to the power x1. This is for x1. That's for xn. And then we end up having a Bayes multiplication there. And you can see this is part that has p. P is our parameter. P is the unknown number in the original model. So then it looks like the sufficient statistics is summation of xi.
Okay.
Okay, so then, so when we look through this example, we realize that sometimes, most of the time, we don't have to have a detailed xi, and we just need to have like a summation or a multiplication or that. Basically, what we need is a sufficient statistics. So for this one. Right, so this entire formula is our model. That since you think this is a Bernoulli, well, let's write the Bernoulli model. And in the model, we have one thing that we want to know, what was the p. And since if you don't know the success rate p, you collect enough data, and then we're gonna look for a way to estimate it. So it looks like this is our likelihood function, called the LP. Okay. So in here we realize that all information is. There's nothing to factor. Factor 1 is like not factoring at all. But anyway, after we combine the power and into summation, we realize the summation of xi is the one that contains all the information for p. So the summation of xi is what I consider a sufficient statistics for p. Question? I mean, do you remember the estimator? The estimator was summation of xi over n. Remember? That was the estimator for t. So the sufficient statistic is not the formula to calculate t, but it's the most important part of the formula that allows you to calculate t. So sufficient statistics seems to be relatable to the maximum likelihood estimator, at least to the likelihood function for formation. But they're not identical, they're not exactly the same thing. But I have to see the method for sufficient statistics is not as time consuming as a maximum likelihood estimator. Because in that one you find the likelihood function, you have to go ahead and find the derivative, you set the derivative to 0, right? The algebra is not complex, but it's still more time consuming than just factor the likelihood function to a certain point. So that's our third example. And are we okay so far?
Yeah, I'm good.
Okay, so so we go ahead and look at try to analyze that probability that we had. All right, suppose you were given a y value. What was the y definition? Oh, y is a summation. So obviously, since we knew the y, which is summation of xi, is a sufficient statistics, if you have a y value, could we possibly calculate the p? So, and here we're going to try to find the conditional probability of p. Conditional probability of, suppose you have the y, what would be the probability x1, x2, and xn? So here we're going to try to find a conditional probability. According to the conditional probability formula, this conditional probability is calculated by the denominator should be the condition, probability of the condition event, and numerator should be the joint event. Okay, so the numerator should be calculated with a joint probability distribution function, the multiplication without all that. Denominator have a y being number of success, which is total number of success. You can do a binomial distribution. We end up getting this number, and that's the 1 over NCY.
I have a question.
Yes.
The reason that the numerator is the way that it is because the conditional probability form is like the probability A given B. It's equal to probability A intercept B divided by probability B, right?
Yes.
And probability A intercept B in this case are the same, so that's why it's like that, right?
Mm-hmm.
Because they're the same function, basically.
Right.
Okay.
Because the y value is given by those x1, x2, xn. So if you have x1, x2, xn, of course the y equal to that summation.
Okay.
So no issue. Any questions?
Nope.
I feel like the rest of them together cancel all these.
Yes, because they're the same function.
Yeah, same function, same power. The only thing was left over was that coefficient.
Yes.
Okay.
Because
so
the y is a Bernoulli distribution, or binomial.
Y is a binomial.
Y is a
Each
binomial.
one of the x is a Bernoulli.
Yes.
So that we end up left over with 1 over the binomial coefficient. That was NCY. All right, so this is saying that given the y value, conditional probability of having all this x's, it does not depend on p. Okay, so in the final result, there's no, the p was canceled. So given the y, then all you have is y, and then there's no p left. All right. So this gives us the, so we're now trying to figure out a formula for the sufficient statistics. So earlier we let's factor the likelihood function, let's factor the joint probability density function. Now, since each one of those sufficient statistics takes on certain formats, so we decided we want to find a common way to identify the sufficient statistics. So from all the previous examples, we identify a certain format. So you can see all those have exponential, can be written in the exponential form. So the exponential form can be written as the way that part of it has your theta, and part of it has, this is the part that has only the x, and this is the part that only depend on theta, and this is the part that depend on theta and x. So if we are factoring, if this is your joint probability density function, as you factor this, you're getting 3 factor like e to this times e to this times e to this. Okay, so here, if you have anything that's not exactly exponential, you can convert it to exponential by this kind of method. And this is writing all the previous one as into exponential form. What was the exception? So for all 3 of these examples, summation of xi is a sufficient statistics. Okay, so we generalize then we have a result saying this. As long as your joint probability density function not joint density function, the individual joint density function. We don't even have to look at the joint density function anymore. You just look at the individual density function. Suppose it has this format, then we have the conclusion that the summation of k times summation of the function k is a sufficient statistic for theta. Okay, so the proof of this is that suppose your this is the density, so your joint density will look like a bunch of multiplication of this. This is our multiplication. E2, there's a summation there. So if you have E2 this for each xi, and then you in your joint density function, you will be a summation of all this. So you have n of this, summation of this, and summation of this. Since this one is correlated, we're related to the n, and p of theta has no connection with n, so that can be factored out as a common factor. So you have summation of this, summation of this, summation of this, which ends up getting you this. All right, and then we can factor this into, this is one factor, and that's another factor, and this is a part, this is a has theta in there, and this is the one that's factored that has no theta. So in this one, the one that part of this formula that actually has connection with x is this part. So that's end up being our sufficient statistics for theta. All the other ones are part of formula for theta, and you can solve for theta from this equation anyway. Any question?
No.
All right, so I mean, suppose you were trying to maximize the probability density function, you would probably maximize this part, since this part is related to the theta, so, and then you can maximize this part since it's an exponential function, so you can solve this as a, after differentiation, you can solve this as a function of theta, and this is probably going to be part of your formula for theta.
Okay.
And it's the idea. So what this theorem does is that it actually saves us time spent on trying to analyze the joint density. You can work out the individual density instead of joint density. So before you see, we have this example. We're saying that after you multiply, you realize that will be the case. But then now we can work individually the individual density. You can write this as exponential into exponential form. And there will be, we're changing the base e to ln t x, right? And this will be e to ln 1 minus b and then 1 minus x. Then we move the one that has, well, they all have theta. So summation of x will be part of the formula, I think, because the power part. I think each one of them have a similar format. Like this is already multiplied, but if you did not multiply, and this will be root of 2 pi, and this will be negative e to the x minus mu squared over 2. How do I get mu? It's already in exponential form. I guess you have to square, you have to extend that to see the summation of xi. Anyway.
Can you do an example of using, is there an example in here?
Yeah, I think we have. After the theorem is being introduced, this is application of the 6.7. Like this.
Mm-hmm.
So suppose we have a bunch of data for exponential distribution. So we have a random sample of size n from an exponential distribution. In exponential distribution, theta is the boundary that we want to estimate. So now, so remember before we have to multiply a bunch of these to get the likelihood function. Now, according to this, we don't have to do that anymore, but you do have to convert it to a total exponential form, exp form. So what we're gonna do is.
What's the difference in k of x and s of x?
K is
So K is being multiplied by a function of theta, basically? Is that the difference?
No, K of X is a function of X, any function of X.
Okay.
K can be X, K can be X squared, K can be 2X, whatever is multiplying part of theta.
And what's S of X?
It's a function of X with no theta in there.
Oh, okay.
And then you have another function with theta.
Okay.
So I guess we can see that with this example. And then, for example, we're looking at exponential.
So in this case, S of X is 0 because there is no just X function by itself.
Let's see. In this case, so we try to rewrite this. We're hoping to write it into. Remember, we wanna. Let's write. Well, so we can annotate. We want to write that into exp of this three-different form. One is you have function of x multiplied by a function of theta. What was the notation? P theta, Q theta. Okay, so multiply by P theta, whatever function of theta, plus one that has only x and no theta, and plus the one that only has theta.
Okay.
So the KPSQ, they are just the name of the function. It's a hypothetical way. So we wanted to see, this is your exponential function. It doesn't look like that form. So we're going to try to convert it to exponential form. This is already in exponential form. It's just 1 over theta we have to convert. So you would write e to, I mean, e is the inverse of logarithm.
Yeah.
So you have e to the ln of 1 over theta.
Which is the same as negative.
Yeah, which is the same as e to the negative ln of theta. And since this one is already have that power, this one has this power. So after you combine them, this is going to be e to the negative ln theta minus x over theta. That's what it looks like, right? So you can see that this x times negative 1 over theta is the negative x over theta, and then we have negative logarithm theta. So in a way that this is equal to, f is equal to exp, and then we have x times negative 1 over theta minus ln of theta. All right, so then the ln theta matches the q theta, which is a function that has only theta, and then negative 1 over theta is the p theta, and the kx is really the x. So that's all the term. As you can see from the theorem, all we need is the k theta, the one in the theorem.
Yes.
It's the one that multiplies the power theta. That's the one that we are concerned as a sufficient statistic. The rest is like part of the formula, but they are not related to theta. So the one that contains the most information for theta is k theta. So in this case, since our k theta is the theta, that's our k theta, kx equal to x, right? Kx equal to x, and by the theorem, summation of the x is going to be, that's going to be our sufficient statistic for theta. And we know that from section 4 that summation of xi is the estimator for theta. So x bar is summation of xi over n. That's also sufficient since it has this one. So that's another thing to say, that the sufficient statistic is not unique. You may have this is unique, that's sufficient. That's also sufficient. That may also be sufficient. You have a question?
Yeah, are all maximum likelihood estimators sufficient, but not all sufficient statistics are maximum likelihood estimators?
Yes.
Okay.
Yes. So see, that's the maximum likelihood estimator, and that's not. So maybe you can use the sufficient statistics to create maximum likelihood estimator, but that itself may not be. But we still want to go this route because the sufficient statistics is more versatile, and then I believe in this section, if you have sufficiency, it leads you to a maximum likelihood estimator.
Okay.
So that's one example. And you can see analyzing the density function seems to be key steps in sufficient statistics using the theorem. All right, so this is a discussion on the relation between the two that you were saying that what was the relation between the maximum likelihood estimator and sufficient statistics. Okay, so you can see that the sufficient statistics is not it's not unique. All right. So if the maximum likelihood estimator is unique, then the maximum likelihood estimator is a function of the sufficient statistics. So here we have, I mean, this is from the definition for sufficient statistics. We realize it has underlying connection, right? The way we identify sufficient statistics is by factoring the maximum likelihood estimator, maximum likelihood function. All right, so here you have part of the function does not depend on theta, part of the function depend on the theta.
I have a question.
Yes?
I thought we minimized the likelihood function.
Well, it's called maximum likelihood function.
But like, okay, I must have been thinking about it differently.
So yeah, we maximize the likelihood. We want to find how, what would be the value of theta to make the probability of getting this set of data most likely.
Okay.
Because you already have the data, that's why you want
I see.
the likelihood to be as big as possible. I mean, according to our method by calculus, the solution is supposed to be, if the solution is unique, then it should be a function of the sufficiency. Because the way we determine the sufficiency is the method itself actually connected to maximum likelihood estimator. Now if we have two parameters, and what would we do? What would the procedure? So again, you have to have your drawing density function. You have to factor it until you have part of the factor does not depend on theta 1, theta 2. Part of it depends on theta 1, theta 2. So if you have two parameters, you may have to have two estimator or two sufficient statistics, which is called joint sufficient statistics for theta 1 and theta 2. Okay, so for that we have one of the examples that definitely have two parameters would be the normal distribution. So here we have an example of it. And the earlier method 6.7 was the one if you have only one parameter, that's if you have two parameters, then we're going back to the multiplication of all these density, and we have this. We have two parameters. One is the mean, one is the variance that needs to be estimated. Again, we have to do. We'll have to
convert it to exponential form.
Oh.
Do they convert it to exponential form?
It's already in the exponential form.
Except for the 1 over
Right,
2 pi
except
theta.
this one. Yes. And if you convert it to exponential form, that's what it is. We use the log, we can convert it to. Is depending on theta 1, theta 2. And there's a lot of algebra involved in here. It looks like the entire thing is depending on theta 1, theta 2. You see the other factor is 1. And so all the other ones that most of the effort is trying to combine the variables. So I have one, we have two. We need two sufficient statistics. So we're defining this one we are calling it y1. That's y1, and that's y2. So now we have a y2, and that's y1. The rest are just related function with theta 1, theta 2. So those two is sufficient. And therefore, a function of those two, like this is a function of the y2, and this is a function of y1. These two are also sufficient. And you can also create other ways. Any questions? Yes.
is the X bar, is that from the definition of the mean of a normal distribution, and the S squared, the definition of the variance from normal distribution?
That's the definition for sample variance. This is the definition for sample mean. Because that's how like 2 is being defined. And
Oh, right.
1 is being defined.
Okay. I see.
We sort of try to connect them. These are the first moment, that's the second moment. So that's the first moment divided by n is x bar, second moment and first moment combined, that's the x squared.
Okay.
And we can also try to find the transformation. This is transformation from x1, x2 to y1, y2. We can also convert from x bar to the y1, y2. So we have this is the inverse transformation between the two set of variables. So one way or the other, the connection. Any question?
If variance is expectation of x minus expectation of x squared minus, expectation of x and then squared, why is there that divided by n minus 1?
Oh, I think this is because
I'm not sure exactly where it's coming from. All right, I get x bar, but I don't get the definition for s squared, because s squared is sample variance, right?
yeah. I think that has something to do with we had this before. That again. All right. Earlier we were saying if you're trying to calculate expectation of x squared, it would equal to sigma squared, right?
Yes.
And that's why we're saying this is unbiased. And again, you're gonna look at the calculation of the expectation is expectation of y1 minus y2 squared over n minus 1. I think we went over this one time. It may be in the last section. This is a definition for y1 is summation of xi squared and y2 is summation of xi. We're going to square all sides over n. I think this was a simplified formula for it's a simplified formula for the x squared. Or this formula was simplified from a more complex, more definition formula. It was the summation of xi minus x bar squared over n minus 1. Right? That was right?
Mm-hmm.
Was an earlier formula there. I think what we had was
Oh, and that's why it's divided by n.
it's divided by n minus 1. What I remember is that we gotta calculate xi minus the population mean, and then plus the mean minus x bar. So we're gonna insert that over n minus 1, and I think you right?
Yeah.
So we were supposed to divide it by the standard deviation, and this also right as standard deviation. So the process of converting it to a standard normal distribution. You have to go by the definition for the variance itself. It was defined by summation of xi um, minus the population mean square over the over sample size n. Now this are this is a minus the x bar. I mean the x bar is actually defined over there. I think if you're using the sample mean to replace the population mean, if you lose degree of freedom. So if we have this, we what is it? Expectation of this was the proof of this.
So since another definition for sample variance would be the summation of x squared divided by n minus or summation xi squared divided by n minus the mean squared, right?
Right.
So we could rewrite it in those terms, right? We could rewrite it as y sub 1 divided by n minus y sub 2 over n squared, right?
No. This is a definition for sample variance. I mean, yes, you can. Yes, you can. If you're saying that you can divide this by sub n.
Yeah, divide that by n and then subtract, and then can I just write it up on the board?
Yes, of course. There's the marker.
So s squared is also equal to right? Because isn't that like basically this? Although I know this is like, but can't you calculate sample?
This is a sample variance.
Yeah, but that's where like this idea comes from. Like this is like the sample. This is like the sample version of expectation of x squared, and the sample version of expectation of x squared. But this is a definition for sample variance, right?
No.
It's not, because I've done that before and it was the right answer on calculating sample variance.
I think that was the definition for population variance is all the data that you had with those numbers. So, for example, if you have xi, the entire population has 100 data. You add up those 100 data divided by 100 and minus the mean of the 100 data square, and this will be the same.
Oh, so it only works if you sampled the entire population?
Right.
Oh, okay.
So if you have a small sample, like you only have 5 data, then if you calculate this, then it will be slightly smaller than it's going to be.
Okay.
We have to count this will be, this will be biased, but then we hope it to be not biased. So we actually divide by the We have actually divided by n minus 1.
Oh, so you just divide this by minus 1 in its sample variance?
No. The formula for there is, it's supposed to be summation of xi minus xr squared over n minus 1.
Oh, okay.
So I think if you have to divide it, it's going to be summation of xi squared over n minus 1, plus minus the summation of xr squared over n minus 1. Yeah, kind of like this.
Oh, okay.
So that's, I think I have to work out the proof of it, but the differences for sample variance with the population variance is at n minus 1.
Okay.
That's why I try to insert a mu there just to complete the proof. I think it's a lengthy proof if you have to prove the mean of this actually equal to the variance squared. So we have to, from that, it's a little bit harder, so I want to go back to the original definition for simple variance to prove it. The mathematical proof, okay, you have to replace it by the population mean, and I have to prove the mean of those two.
Okay.
All this time.
Yeah.
But I'll give you a complete proof for next time, and we have to separate these two and find the expectation for this, and find the expectation for the other one, and combine them, and that's where the difference is between the mu and the xy.
Okay.
Any question?
No, it's possible that
This is not that big. I mean, if you use n minus 1, it's very similar if the n is large enough.
okay. So like maybe before I done on homework problems, it just happened to be the correct one when you round it, because the book answers are rounded, so that's probably why that's the case.
If you find out the actual question, maybe it will be more specific.
Okay. Yeah, I'll try and figure that out.
That's it for today. Thank you.
Thank you.
Let me
I'll
have,
see you in a few minutes.
yeah.